This video is a sample from our ASReml-R course Mixed Model Analysis of Medical Data, which uses real-life datasets from an array of clinical studies. The full course covers matched case control and multi-center studies, crossover trials, meta-analysis, and random effects regression models, among others. At the end of this video, I'll show you how to sign up for the full course and instructions on how to get a 50% discount.
Repeated measures analysis is a very important type of analysis that we do in many studies from medical and biological sciences. The main characteristic is that we are going to evaluate the response over a period of time. Therefore, we're going to measure the same experimental unit, which could be a patient or unit, over a period of time. In this case, we have the patient evaluated several times over the study. This is often called a longitudinal study. And as I indicated, the time is going to be very relevant because we want to evaluate how this response has changed or has not changed over time. In order to draw conclusions, we will analyze all the data set in one go. Sometimes you analyze every single period of times individually, but the idea in repeated measures is that you analyze everything together in one go. This means there might be some imbalance, but this is usually not a problem under the mixed model theory with the restricted maximum likelihood. Because we are measuring the same individual over and over, we no longer have this assumption of independence. Therefore, we have to change the way we model this, and we need to consider this lack of independence into our residuals. We do that by considering or incorporating a correlation matrix or a correlation between the measurements of the same experimental unit or individual. And this has to be done through the linear mixed model, and we need to estimate this correlation structure. Now, we do this correlation structure by defining a matrix R. This is the matrix of variance-covariance between the residuals. In the off-diagonal, if we have only zeros, it means these observations are independent from each other. But if we have something different than zero, that means we don't have this independence, and we obviously need to estimate those covariance components in different ways. So, for example, we have different structures, but here I'm just showing three of the most common structures: the AND structure, the autoregressive of order 1, and something called correlation, general correlation, heterogeneous. Let me first focus on the AND structure, which is the most generic one. Assume we have 4 periods of measurements, 1, 2, 3, and 4. So this represents the variance on period 1, variance on periods 2, 3, and 4. So we're assuming these variances are different, therefore we're assuming heterogeneity of variances across the periods. Now, in the off-diagonal, we don't have zeros. We have these covariances, 1 and 2, 1 and 3, etc. And those, because they could be positive or negative, are the ones that are going to model that correlation. They need to be estimated on the whole model, but they're allowing us to have different covariances and therefore different correlations between different pairs of measurements. One very common model that is used in many of the repeated measures analysis is the autoregressive of order 1, which is easier to fit because in contrast with the UN, it has only 2 variance components to be estimated, and notice that the UN had 10 variance components to be estimated. Now, what's the characteristic of this one is that we have a single variance across all the periods, so assumes homogeneity of variances, but this can be also made more flexible. And we have a correlation, rho, which is the correlation between consecutive periods. So in the rho 1 means rho to the first power is the jump from period 1 to period 2. Now here is rho square because there's 2 periods. We go from period 1 to period 2, then to period 3, and then similarly for this one. This is a very easy to fit structure. You'll find it in most of the software. Core GH is just another parameterization of the AND structure. Instead of being modeled as covariances, we model this through this correlation, rho 1, 2, 1, 3, 2, 3, etc. So it should give exactly the same results, and in general, this is a bit easier to interpret than the UN. Now, there's many other structures, some of them with different restrictions, with different parameterizations, so you should be looking for all the pool of different options. This data originates from a randomized double-blind trial on which we are interested in evaluating the grip strength of different patients that have rheumatoid arthritis. These patients were assigned randomly to 2 different treatments, T1 and T2. Now, these patients were measured 4 times. At the first visit, the treatment was not applied, therefore this is just the baseline. But during the other 3 visits, we have the actual measurements, and we can assess how the treatment behaves over time. So the baseline is going to be considered as a covariate, something we need to control for. In addition, we suspect that some of the males and females were going to respond differently for the grip strength. Hence, we will need to include this covariate of gender to differentiate between males and females. And potentially, we have an interaction with treatment that might be different between males and females. So the objective of this study is to compare statistically the 2 treatments, T1 and T2, but also to see if we have some potential interaction. Now let's see if we can look at a little bit of the data. And here we have all the individuals. We have an ID for the observation, subject, all the way to 79. Not all the subjects are here, so those are their codes. The baseline measurement is 120 for this patient. Notice this will be like the time or the period 0. And this is the measurement for period 1, 2, and 3, which are identified here as 1, 2, and 3. This patient was assigned to treatment T2 and corresponds to a male. So we have sorted by patients, and then within patients sorted by measurement, by period. And we have lots of cases. For example, this one, we have a patient that was measured on the baseline with 40, first treatment 60, and then is missing for the others. That missingness is going to affect us with some of the standard errors. It doesn't seem to be too serious in this particular data set, but in others it could be more serious. So let's proceed to try to analyze this data. So obviously we have different approaches, but one of the main things we want to do originally is to try to first look at the data and have some expectations of what we're going to find. So I'm going to read the data. I'm going to use the library ggplot to make some nice and more fancy plots. I'm reading the data here. This is just what we saw before. I'm going to do some exploratory analysis so I can pretty much calculate the means. In this case, I'm calculating the mean for the combination of treatment period. So we can see here on treatment 1, 139, and the other one started with 141. 42, 47 seems to go up, and this 49, 40, and then seems to be go down. So there is some structure going there. This is just for me to help me where do I have every patient. Every patient is measuring everything in every period. Obviously we have some NAs, but at least we have the data balanced in that way, and that's very important to fit the software. So by gender we have some combination. We have males and females assigned to the different groups. We seem to have more females than males in this particular data set. So now I'm going to do 2 graphs. This is one graph in which is showing me the different treatments and the lines by subject. So we can specify this in this statement on group subject, and it will make the lines. And then the colors associated with the lines will correspond to the actual treatments. So in this particular case, we have the lines for the different treatments, and you can see a little bit how it happens to be a bit more blue, seems to go more to the high, and there's a lot of crossing over. So the ways these are changing is quite variable between the periods, and the patients are changing quite a lot. So that gives me a little bit of an idea. The second one, which showed me the same thing, but just by gender, which again is quite useful because now we can see that the males tend to be considerably much higher than the females. So that's pretty good. So now we can start with our analysis, or before that I will create my factors. So let's just see, we have ID, subject, baseline, treatment, gender, and period. And we need to make some of these factors. Grip is my response, but period has to be a factor, and the subject has to be a factor, and obviously treatment has to be a factor. So now we're ready to do some of the analysis. So one good way to start with this is just to do a single period analysis, okay? And this is useful in order to assess how each of the periods are doing. Or we have, for example, outliers. So I'm just going to analyze the period 3. And we have to think a little bit what is the structure of this model just for period 3. And in order to do that, I'm going to go back to the slides and just think about what will be the linear model for a single period. So what we have is we have a response variable, we have an overall mean, we have the fixed effect of gender, which is our covariate, male or female. And now I have another covariate, which this is a continuous covariate. This is a factor, male or female, but this is a continuous covariate, which is associated with the slope, and this corresponds to the baseline, and it's going to make a correction depending if you started on period 0 too high or too low, and that's just its role. This is not very relevant in our terms of analysis because they are covariates. More relevant for us is alpha, which is the treatment 1 and treatment 2, and then we have the interaction between treatment and gender. So we can proceed to analyze this for a single period. So my response is going to be grip, and then my fixed effects need to be, as I indicated there, gender, baseline, which is our covariate, and is going to be treated as a continuous. Here is as an integer, and then I need my treatment, TRT, and treatment by gender. I will do it gender by treatment. I have no random effects in this model, but if I put data equals to grip, I'm going to use all data set, and that's not what I want. I want a subset. So ASReml has this function subset where we just indicate the factor equal, and then in this case I'm going to say 3, which corresponds to the period with the level 3. So I can analyze this, and I can actually pull some of the summary statistics for this analysis. So first I'll do a plot, as we have done in many other parts, and we can see if there's a potential residual, decide if we want to eliminate something. We have information about the variance component, which could be critical to have an idea of knowing if all these different periods change too much between periods. But the most critical for us is going to be obviously the wall test. We are going to P3, we're going to say then df, it's algebraic or numeric, and then we say SS type equals conditional. So when we proceed with this, we have a little bit of an idea. We say gender seems to be not very significant. The baseline seems to be significant. Now this is saying really that there is a correction from the baseline that is important to incorporate. It's obviously telling me that the slope is significant, so that means the baseline is affecting what happens. Then we have the treatment, which it says is not significant in this particular period. And then we have the interaction, which is not significant. I could easily change this to a 2 and run this for the period 2 and continue just assessing what happens. So this analysis pretty much does all of that. Now I can proceed to do some more complicated things. So now I'm going to do my repeated measures analysis. So I'm going to aim to model what happens with R, and I'm going to be very ambitious. I'm going to use a core GH. Remember, the core GH is going to be the model that models all the repeated measures for all the periods. So I'm going to just copy that, but I need to modify it, of course, and I'm going to call this core GH. Now the key point here is that now we have the different periods, therefore this shouldn't go here. And now we have to say, oh, there is a period, which means that each period has a different mean. The period should interact with gender, because each period has a different effect of gender. Each period has a different baseline effect. Sometimes we use a common baseline effect. In this case, we'll have to use a common baseline effect because everything is the same. Then we have a treatment that it's across everything, but we also have a treatment that will be by period. And the same thing will happen with the gender on itself or by period. So what I'm going to do is I'm going to add a few things. This is my original model, and this is the baseline. But now I can add a different mean, and I'm going to add here, I'm going to add a period, which means now we have different means per period, but I need to add period treatment. There's no point in putting period baseline because all the values from across the same periods are the same baseline value. So now I have period, I have made period interacting with this. I can make period interacting with gender if I wanted to see difference on gender, and I can make period, so I can make period interacting with gender, and finally I can make period interacting with gender and treatment. So period, gender, treatment. So this seems to be okay. I don't have Any issues? Now, some people decide not to put the period by gender. Some people might decide to put other elements, and that's up to you. And now the most important is that we need to specify what sort of residual treatments we have. We will say, okay, I have all the subjects, and this is the easiest way to say, and they are going to be, by subject, I want to do something across their periods. So the way we think about this one is we say, well, the subjects are independent from each other, but the periods within the subject are not independent with each other. That is where I say I want a core GH for those 4 periods, or in this case 3, that I have within this data. So we can try to analyze this, and it says obviously it needs a little bit more iterations, so we can easily fix that. Core GH, and then we use update ASReml. This is an ambitious model, so it should more or less run. There it is. Now, before I go there, I'm just going to go back to the model with the multiple periods so you can see a little bit what's happening. I have added the period, we still have the gender, we have the covariate with the baseline, I have the treatment, and I have the treatment with gender interaction. I put treatment by period, and this is a 3-way interaction, and in the model I'll just show you, I also add the gender by period, and often this one ends up not being significant. One key point is that the errors are being modeled with a matrix R, which is what I just have done with the core GH. And recall, the core GH, what it's doing is modeling this way. We have 3 periods, so this will be a 3 by 3, where we have different variances and a correlation 1, 2, 1, 3, and 2, 3. And let's see if that is what we get from the variance components. So I'm going to do more model core GH, and we can see the variance component. And this is just a baseline reference. We have a correlation between 2 and 1 to be 0.4, 1 and 3 0.32, and 2 and 3 being 0.79. So they are a little bit different. They have relatively big standard errors because there's not much data. And notice these are the variances of the different periods, which tend to go higher as we move along, which is interesting. So that means the response changes across the time. So again, what we can do is we can do the wall test. So I'm going to do core GH, and then will be very similar to what we have before, but notice now that obviously we have denominator degrees of freedom associated with all the observations and with their structural correlation. The denominator degrees of freedom is not 201 minus the fixed effect. It has to be adjusted by those correlations. If you recall, before we have in our ANOVA, we have 53, which corresponds to just analysis of one element. In this case, we're analyzing everything together and we have strong correlations. So we have significant effect of gender, we have significant effect of baseline, we already knew that. And then we have probably the only thing that seems to be something period by gender, but none of the other interactions seems to be very significant. So the treatment seems to be not doing much. We can extend this to just look at the predictions for the same model. And here we can classify or request this by something that probably will be the most reasonable one, which will be treatment by period. So I write period treatment. If the data is unbalanced, this is going to give us a little bit of problems. Otherwise, what we'll get is we'll get by period and treatment, the means, there are standard errors associated with them, and this is what we can use to draw some conclusions. Now this is pretty good. We have a good model. Let me just change this to a more traditional autoregressive model. The reason why we want to do the autoregressive, and I'm going to call it AR1H heterogeneous, is because we might have too many periods to measure, and then this core GH is difficult to measure, so we use a simplification. I can say AR1H, and the only thing I do here is I change this to AR1H. Now it's very similar to AR1, the only difference is that we allow a variance for each of those periods. And the reason why I do that is because I seem to have evidence that this increases over time. So let me just analyze this one, and then we can call AR1H. We don't need to actually reiterate. This one seems to have fit in one go. AR1H. And then we have a single correlation, 0.596. And this is the correlation, let me go back here, between period 1 and 2 to the first power, 1 and 3 we'll have to square it, and 1 and 3, yeah, and 1 and 4, and we have to put the cube. So this, it's just one single value. It has a relatively small standard errors. Notice what we had before. We have much larger standard errors, not in all the cases, but in some of the cases. So because we have less information to estimate, this is estimated with everything together. And again, the variances tend to increase pretty much as before. We can proceed to do the same thing. We can do AR1H for the wall test, which is not changing too much. There's some difference on the p-values because the structure is different. And then again, we can also proceed with our predictions across the combinations of periods and treatment. So just for the sake, I can use an AIC or BIC in order to compare the models. And this is done by using the summary of the model, score GH, and then we say AIC, if I recall very well, yes. And that's the AIC for the first model, and this is the AIC for the second model, AR1H. And then we can proceed to select which one of these two models is the better. So with this, I've shown you a few of the structures that we can analyze, like repeated measures. There's a lot more information in the literature that I recommend you revise.
I hope you found our video useful. If you'd like to see the rest of the Mixed Model Analysis of Medical Data series, you can sign up for our course and get 50% off by clicking the link in the description below. Thanks for watching.